Welcome to This Explainer. Today, we're diving into one of the most fundamental, honestly, kind of fascinating components in modern electronics, the capacitor. We're going to peel back the layers and look at the invisible tech that's literally powering our lives right now. From the smartphone in your hand to the massive power grids keeping our cities lit, let's get right into it.
To kick things off, I want you to think about this for a second. What exactly allows a camera flash to go off instantly, with that huge, blinding burst of light? I mean, it happens way faster and with way more intensity than a standard battery could ever pull off. So how on earth does the camera summon all that power at once?
Well, the answer lies in a pretty great comparison. Think of a battery like a marathon runner. It gives you this slow, steady, long-term energy over hours or even days. A capacitor, though, it's a sprinter. It's built for one thing: delivering insanely fast, temporary bursts of power. So unlike a battery, a capacitor only holds on to energy for a very short time, and it's specifically designed to charge and discharge almost instantaneously. Formally speaking, a capacitor is a passive electrical component that stores energy in the form of an electric field. It pulls this off by trapping electric charge right between two conductive plates, and those plates are separated by a special insulating material that we call a dielectric. It just temporarily holds onto that charge, and then boom, it releases it the exact microsecond the circuit demands it.
If we look at the physical anatomy here, those conductive plates are usually made of metals, like aluminum, copper, or silver. But the real magic? That happens right in the middle. The plates are physically separated by those insulators I mentioned, the dielectrics. Depending on what the capacitor is used for, engineers might use air, paper, ceramic, plastic film, glass, mica, or an electrolyte. Sticking this dielectric between the plates actually boosts the capacitor's overall ability to store that electrical charge.
Moving on to Section 1, the mechanics of electrostatic induction.
Okay, let's zoom in and see how this actually builds step by step while charging. First, you connect your capacitor to a direct current, or DC, source. Current starts flowing, but because of that insulating dielectric in the middle, the current can't jump the gap. It hits a wall. So electrons start piling up on one plate, making it negatively charged. At the exact same time, the opposite plate is losing electrons, becoming positively charged. As this builds up, an electric field develops between the two plates, and the voltage across the capacitor climbs. Finally, the charging totally stops the exact moment the capacitor's voltage matches the supply voltage. At that point, it is fully loaded and ready to go.
So, what happens next? This is the crucial part. When you take away that power source and hook up your fully charged capacitor to a load, say a camera flash bulb or maybe an audio amp, all that trapped energy finally has a way out. The stored charge rushes out rapidly through the circuit, and as it dumps all that stored energy, the voltage gradually drops until the capacitor is completely empty, totally discharged and ready to start the whole cycle all over again.
We call this ability to store a charge capacitance, and we measure it in a unit called farads. Though out in the wild, you'll usually see it broken down into much smaller chunks, like microfarads or picofarads on those tiny little components. The formula for this is straightforward but super important. Capacitance, or C, simply equals the total charge, Q in coulombs, divided by the voltage, V. Now, if you want to calculate the actual raw energy stored in joules, we use this really elegant formula. Energy equals half the capacitance times the voltage squared. Basically, this tells us that if you crank up the voltage across a capacitor, the amount of energy it stores shoots up exponentially. It's pretty wild. It's this tiny physical space holding a surprisingly potent electric field. All right, Section 2, behavior in AC versus DC circuits. Let's see how these sprinters act in different environments. This highlights a massive difference in how they operate. In a direct current, or DC circuit, a capacitor charges up fully and then, well, it basically acts like a brick wall. It entirely blocks any further steady current and acts just like an open circuit. But throw it in an alternating current, or AC circuit, where the current is constantly and fluidly switching directions, whole different story. Because the current is alternating, the capacitor continuously charges and discharges. So in an AC circuit, it actually lets the alternating current pass right on through, which makes it absolutely incredible for filtering signals.
Let's move to Section 3, capacitor variations.
Just take a look at this table. It really synthesizes the sheer diversity of the capacitor family. You've got ceramic capacitors. These are tiny, dirt-cheap, and non-polarized, meaning you can plug them in either way. They are perfect for high-frequency radio circuits. On the other end, you've got electrolytic capacitors. Now these are polarized, so they have a strict positive and negative terminal, and they pack a huge capacitance for heavy-duty power supplies. There are glass capacitors built to survive insane aerospace temperatures, and even variable capacitors where you can manually adjust the capacitance. That's actually exactly how older radios tuned into different stations.
Now, while capacitors are highly reliable, super low maintenance, and extremely fast, we do have to keep their limits in mind. First off, they hold very limited overall energy compared to batteries. Remember, sprinters, not marathon runners. Also, their voltage drops steadily as they discharge, which just isn't ideal for every type of gadget out there. Crucially though, they are fragile. They can be physically damaged if you hit them with an overvoltage, and for polarized types, like those electrolytic ones, hooking them up backward will literally destroy them. Finally, let's wrap up with Section 4, the real world and safety.
You might not always notice them, but trust me, capacitors are absolutely everywhere in your daily life. They're seamlessly filtering the power in your phone chargers and laptop adapters to keep the voltage nice and smooth. They are tirelessly regulating the startup motors in your ceiling fans and washing machines. They power that instant camera flash we talked about right at the start, and on a much larger scale, they are critical for stabilizing renewable energy systems like solar inverters and even electric vehicles. Modern life relies heavily on these invisible little electric fields.
But listen, because they hold energy like a loaded spring, and because they can actually hold that charge long after a device is completely unplugged, safety is absolutely paramount here. You have to always discharge a capacitor before you handle it. Never exceed its rated voltage, use insulated tools for sure, and always double check your positive and negative connections if they are polarized. Oh, and if you ever crack open an old device and see a swollen or bulging capacitor, that's a clear sign of internal damage. Do not mess with it. It needs to be safely replaced immediately.
As we wrap up this explainer, I want to leave you with a quick thought. Look around the room you're in right now. Between your computer, your chargers, the lights, all your appliances, how many thousands of tiny electric fields are quietly paused all around you? Just holding onto their electrons, waiting for that perfect fraction of a second to unleash their energy. It kind of makes you look at the electronics around you in a whole new light, doesn't it? Keep exploring, and thanks so much for joining us for this explainer today.